Now for our first keynote talk of the Flight Software Workshop, it is my pleasure to introduce Steve Thibault. Mr. Steve Thibault serves as the Chief Engineer in the Space Exploration Sector at the Johns Hopkins University Applied Physics Laboratory. Mr. Thibault has over 30 years of experience in space systems development, production, integration and test, launch, field campaigns, and mission operations. Mr. Thibault joined JHU-APL in 2006, making important contributions on several robotic spacecraft and instruments while holding line management roles in power systems, component and materials engineering, and integration and test and mission operations. Prior to joining JHU-APL, Mr. Thibault led the satellite manufacturing at Orbital Sciences Corporation with specific contributions to creating its geostationary communications product line from inception. He started his career at Analytics Services working on advanced launch systems and exo-atmospheric interceptors. Mr. Thibault earned a bachelor's degree in aeronautical engineering from Rensselaer Polytechnic Institute, a master's degree in applied physics from Johns Hopkins University, and is currently in the dissertation phase of a doctoral degree in materials science and engineering from Johns Hopkins University. Welcome, Steve Thibault.
Hey, Chris, thank you. Can you hear me well enough?
We can hear you and we can see your slides.
All right, well, I will share video, which I think you can see now too. All right, so thank you for the opportunity to speak at this year's Flight Software Workshop. When I was approached by Chris as the APL host about potential interest in speaking, my first thought was, as a hardware systems developer at heart, what would I speak about to a software community? My second thought was that this is a great opportunity for me to discover a vision for software advancement in space that I could then promote within APL as its chief engineer. And then I realized as a long-term developer of robotic spacecraft that I actually might have a vision of my own, or portions of a vision for software that could benefit this community, and then in turn benefit me in systems development through the realization of a shared vision. Next slide, please. So I resonate with the old story, which I'm certainly going to embellish, but it sets a foundation. So two people are walking a street. One is holding a loaf of bread, the other one is not. They reach each other. The person with the loaf of bread breaks it in half, hands one half to the other person. They both leave the street or leave each other holding a half loaf of bread. Whereas two engineers on that same street are approaching each other. One holds an idea. They arrive together, they meet. The one shares the idea, they discuss it. The idea improves. And as they leave, they both hold a better idea. And so in that light, in that foundation, I want to share with you an idea. And I'm eagerly interested through the course of this conference anticipating that we will walk away with a better idea and better ideas. And through better ideas, I believe we will collectively do bold and great things. We are in this together. Next slide. So before I lose the audience attention, the idea. As robotic missions reach for further away destinations, 10 to 15 years of transit time are commonly being proposed for the outer planets. As transfer vehicles boost more life into the Earth orbiting communications fleet, geocom satellites that already carry propellant and solar array capacity for at least 15 years are now being extended for another 15 years. And as we look to return to the lunar surface and use the precious launch mass of bringing resources and assets with us to then increase future capability progressively on the lunar surface, let's implement a flight software for capability that we cannot imagine today. So, capability that we cannot imagine today. Too vague, too far-reaching, too bold, not rooted on the ground? Though I argue that none of us here today are actually rooted on the ground. All of our minds are in the heavens. Otherwise, I submit that none of us would actually be here at this workshop today or this week. So next slide, please. So out there, space exploration via robotic spacecraft is a one-way journey. Out there, beyond, further than beyond, we cannot change the hardware en route. What we launch is what we deliver to that end destination. But we can certainly think of changing the software, and through enhancements and change of software, we can enhance capability and perhaps change the future, and specifically the future of that mission. So if anyone can and is going to implement for capability that we cannot imagine today, it will be this community. You all, the spacecraft developers. And through this, I and my colleagues, specifically those of us that consider ourselves not to be software developers, we will together experience amazing and out there and beyond with future capability that, again, we cannot imagine. Next slide, please. So you might say, really? Some of you are probably actually saying that. Really? Yes, really. A small personal story. 34 years ago this year, I began my career on pencil and paper. Indeed, pencil and paper. Arriving into the space workforce from a premier United States technical institute, after having completed complex fluid dynamics calculations for my senior aircraft design project, using what was a leading mainframe at the time, I was handed a ruled yellow pad of paper and a mechanical pencil of my choice. For those of you not familiar with the technology of that time, ruled simply means lined. So handed yellow pad of paper with lines on it, mechanical pencil, and the programmable calculator that I brought with me. This technology was provided to me in which to take notes, perform my calculations, and draft my reports. To then hand off to a group secretary and get in the queue for typing on a fledgling word processor, to receive paper back, to make edits, and then repeat that cycle sufficient number of times to my satisfaction. To then have that cycle repeated by senior management interested in improving my report product and completing the review process with final edits. And look at us today. We're holding this workshop via a Zoom webinar. Most of us are working from home during this pandemic. Many of us are connected to our corporate networks from home. A few of the software developers on this webinar are probably remotely running tests on hardware as I speak. A very fortunate few from APL are actually testing an asteroid interceptor. Yes, an asteroid interceptor being tested in a thermal vacuum environment by skilled engineers, serving double duty as homeschooling parents, with a small team that are actually co-located with the spacecraft, but with a larger engineering team working remotely. Another even fewer and as fortunate engineers at APL are remotely commanding the Parker Solar Probe spacecraft that you see an artist rendition of as it returns around the sun from Encounter 7, which you can see in the right-hand graphics that I pulled down from the website yesterday. And they're doing that from their homes, communicating through the NASA Deep Space Network. And the one particular location of excitement to me is Madrid. Anyone? And I imagine that another few of us, well, maybe perhaps many, are catching up on email while listening to me speak and wondering when will the hour be over. For you few or many, I apologize for the lost time into your life that you can never recover. But I do think that we can both benefit from the idea here. So 34 years from pencil and paper to engineering collaboration with participants around the world at the same time at the 2021 Flight Software Workshop, discussing an idea or implementing capability that we cannot imagine today. And certainly a capability that I did not imagine at that time 34 years ago. Simply fantastic. This very moment indeed shows the truth of the idea. Next slide, please. And just imagine Interstellar probe. A mission to arrive at 400 astronomical units from us. For those that aren't aware of that definition, 1 astronomical unit, or 1 AU, is the distance of the Earth from the Sun. So 400 times the distance of the Earth from the Sun. 15 years after launch in January of 2006, today, the New Horizons spacecraft is only approximately 50 AU from the Sun. So the very creative engineers and scientists that are conceiving Interstellar probe are striving for a 10 AU per year velocity. So 40 years to get to the final science destination. The same time scale of my personal story of 34 professional years and the amazement in computer and software advancement in that time. What will our descendant engineers, spacecraft operators, and scientists wish of Interstellar probe when it gets there? What will they want to have it perform beyond what our colleagues today are initially conceiving and will develop and launch? What will they need it to perform? As importantly, I think, what training will they have received from their technical institutes, universities, and colleges of the time? Training in some ways that will need to be undone to work with the tools that we leave behind for them. Tools today that are the states of our art, the state of art for our time, but the archaeology of their future time. I think that is worth restating. Our state of the art becomes the archaeology of their time. After launch, 40 years later, no hardware on the Interstellar probe spacecraft can change. All that it can use is what it brings with it. The power supply will be the power supply that's launched. The attitude control sensors and actuators will be the same that lifted off from Earth at launch. The detectors that will be doing exciting science will be the same hardware that is delivered at launch. But what can the software be? With today's paradigm, the software will be what is launched, or at most, any final developments and refinements that were completed by the software development team and loaded to the spacecraft during its first year of flight. And what if in 40 years, advancements in artificial intelligence and other only hoped for and conceived of exciting developments in software are commonplace in our terrestrial systems? What will the future wish of Interstellar probe be when it gets there? Next slide, please. Am I crazy? Success in changing a paradigm benefits from assessing the fatal flaws of the new idea. We need to hear all of the no's, and yes, I did look up to make sure that that is the correct spelling that you see on the screen. But we need to hear all of the no's in order to turn them into yeses. Generally, no one likes to hear a no. I certainly don't. But if change is to occur and innovation to thrive, it is essential, albeit mandatory, to hear those no's early with a commitment that they will be solved. Stopping at a no simply equates to not succeeding. So turn those no's into successes. Turn them into yeses. What are the few of the obvious ones? I can think of three right now as we chat here based on our current paradigms. First, something I live every day at some phase of element of development, and that is classical system engineering B. I'm sure everyone on this call, on this webinar has experience with that development cycle. Requirements get defined, they drive they drive design, design drives fabrication, fabrication then needs to have verification through component test, which then elevates to the next higher level assembly, to subsystem level verification, and then ultimately integrating hardware and software together for integrated system verification, and then through that process, system validation. All that being completed, documented, and reviewed prior to the pre-ship review to then authorize the launch campaign. And then, of course, the launch readiness review to review the events that occurred while the spacecraft was at the launch site to then confirm and verify that spacecraft should launch. So the classic systems engineering B that we all live in our development for spaceflight hardware actually represents an aspect of a no to the suggestion that I'm making. Secondly, cost. Phase E funding on an annual evaluation is the lowest of any other annual or any other year during development. Necessarily so, because if you have, as New Horizons did, 9 years to get from Earth to the Pluto flyby, you need to minimize the annual cost such that when you multiply it by 15 for its current duration of mission, you actually have a mission that's affordable. And so it's going to be an essential discussion if we're talking about designing software capability today in our spacecraft for capability that we can't imagine for tomorrow. And then, of course, thirdly, which is something that resonates deeply with me, the very real concern, a very real risk that we might do something to the spacecraft with a future software enhancement, whether that be degraded capability or, in the worst sense, some sort of catastrophic loss to the spacecraft and therefore the mission. And of course, without question, that has to be avoided. So let's consider a paradigm shift for software development on long-term space exploration missions. And I submit that the same thought piece equally applies to advancements for long-duration Earth observing or Earth serving missions such as geocommunications. And like this spectacular image from Apollo on Earthrise that you see before you, they changed all the no's to yeses, and that's what we need to do as well. Next slide, please. So there's no question that all spacecraft must be launched with validated and verified flight software sufficient for the initial mission. So for the early operations phase of a long distance journey, a traditional development must occur, including a safe and reliable ability to load and execute new software in flight. As an example, a spacecraft moving at 5 AU per year, which is only half that proposed by Interstellar probe, this would mean that that software must meet requirements and concept of operations from liftoff through nominal Jupiter distance, providing additional year of development for the next phase of the mission. For Dragonfly, as you see illustrated here in this graphic of the octocopter that APL is excited to deliver to Titan, it has an approximately 9-year cruise plan to get to the Titan surface. And so surface flight must be successful 9 years after launch. Any post-launch flight software development would then need to follow a focused systems engineering development methodology specific to the future functionality. Still crazy? So we already have practice and experience in just that. Though albeit out of necessity due to development delays, I'm aware of one lander that launched with fully functional cruise software, EDL landing software, and initial surface operations capability. And due to the development delays, to actually be able to meet that launch window, a very strategic and courageous decision at the time was made that the software for the complete surface operations functionality could be completed during the early cruise phase operations, validated on the ground, and then loaded to the vehicle for success. And that mission had fantastic success. So the idea being proposed here, the future software development capability would be pre-planned as part of the overall mission and lifecycle development. And of course, the cost estimates and the cost planning and the schedule development and the staff planning and the staffing leadership would follow from this planning process. And so we would need to, again, keep changing the no's to yeses. Next slide, please. All right. So we can satisfy ourselves that we can conduct phase development. In fact, many of you are probably already thinking that you already do this in a software development environment pre-launch. Any of you that have worked in either an iterative waterfall or agile software development methodology has done exactly this. Initial requirements are specified. Perhaps it's considered build 0 or build 1. Design occurs. Implementation takes place after that. Component validation or unit validation occurs. Integrated validation or verification occurs. You deliver it to the floor, you deliver it to the sponsor, you deliver it to its use. You cycle back into a new requirements definition, added design, continued implementation, continued test. You find changes, you find fixes that may update or influence the design, and it goes back into fabric or implementation, and then ultimately delivery of the final software product. So nothing new here. And perhaps nothing exciting about what I'm saying. And as I look at the clock, we've been listening to me now for nearly half an hour, with perhaps the simple recognition of the idea is that now it's pre-planned for post-launch, and it may occur many years into the future. But how can we be confident that those future flight software developments, and notably the possibility of the impressive advancements ahead with AI, do not pose future flight risk and potential catastrophic loss to the mission? Are we confident with a new flight software load to a mission such as Interstellar probe, say 30 years into the future, post-launch, when the original software developers are likely no longer available, though hopefully with other scientific advances, they're still alive to actually be consulted and see the excitement of their mission having great success in the future. But I think that a future software path, and some here might argue a current software path, for this need can actually follow thousands of years of our own unique success. And that simply is stated as the partitioning of what I will call subconscious and conscious thought and functions for a flight software for continuing the idea and the argument that I'm making here to you all today. So I breathe, I live while I sleep without conscious thought. I hear and I react without conscious thought. That loud noise that catches my attention in the back, I'm not consciously waiting to hear that loud noise at all times. Otherwise, I'm doing nothing other than trying to wait to hear that loud noise. I balance and move without conscious thought. I walk and talk without conscious thought. Well, perhaps I cannot walk and talk well at the same time, or perhaps I can't speak insightfully without moving my hands. But I grow and learn and evolve my knowledge and intellectual ability through youth, into adolescence, through university, and into my profession. And I now am, 40 years later, more than I was before. And never was there a concern by my colleagues or my peers or my supervisors or my professors or my teachers or even my parents that my subconscious thought and function and capability would fail while I improved my higher order thought. So I believe for us, and really for you and the talents that you all bring to software development, that a similar paradigm can offer great success to the spaceflight argument that I'm making. So what are the options or some options and considerations I could deliver on that exploration excitement? And I truly think it is exciting. So I offer a few brief ideas. Layered software applications. I'm distinctly not the expert here. So all of you will tell me where the weaknesses are and what it will take to accommodate something like that. I certainly have questions. And these would be the questions I would ask of any software development team at APL working on such an implementation. Can I protect the brainstem functions while increasing my consciousness, staying with the human brain analogy? Can I sleep and then wake with a higher order knowledge capacity? Where was that 40 years ago? Imagine learning a second language while asleep. Imagine a different outcome on that first calculus test freshman year at the Institute when my head fell asleep on the text because I'm pulling the all-nighter to try to actually pass that exam. What an impressively different outcome I could have expected if I could sleep and then wake up with a higher knowledge capacity. So does that offer a software architectural development path and approach to this idea of implementing for capability that we cannot imagine today? How about partitioning of the computer resource? And of course, working through processor utilization and throughput and memory margins and data bandwidth and timing and sequencing. Of course, all that needs to be worked. So, but where are the weaknesses here? Are there risks of locking up the flight processor with a failed knowledge upgrade? Certainly something that needs to be avoided. How do I safely recover from a failed new load? How do I get back to what I know worked to then figure out how to make what's new and what I need to work to have that enhanced capability? A third idea we're actually already using on Parker Solar Probe, and that's rotating processors. So the computer architecture of Parker Solar Probe has 3 computers that are used in a primary hot backup and spare configuration, and we rotate through those 3 processors. So for 2 weeks, as Parker Solar Probe is at closest approach to the sun, we cannot communicate from the Earth to the spacecraft. A lot can happen in 2 weeks. That exquisite thermal protection shield needs to be constantly fine-pointed to the sun to protect the rest of the spacecraft with all the instruments on, because that's where the fun science is happening. That's the reason for being if you're Parker Solar Probe. But the rest of the journey in that orbit that you saw as the spacecraft leaves its closest approach provides an immense opportunity to load new capability, which then goes to the next processor. And when we're comfortable and confident that that load has occurred successfully, we then rotate to that processor. And after a certain period of time of confidence and comfort in using the new capability, we then load the new software on the other two processors. We've done this now already in the first 2.5 years of successful and exciting mission operations for Solar Probe. And it perhaps shows an important architectural approach for this idea that I'm making the argument for. And then if I think perhaps as a fourth architectural approach to toss to you all for your thought process, we return closer back to the human brain analogy. How about a lesser capable processor, albeit one would expect and hopefully a cheaper processor, that serves that essential function of the brainstem analogy? Of course, if you look at this graphic and you've been reading the functional capability that have been discovered and connected to different parts of our brains, you'll immediately see, well, I have to be able to hear Earth. So clearly I have to have a temporal lobe capability of some minimalist approach. And I have to be able to speak back to the Earth. And so, of course, I've got to have some sort of frontal lobe capability to be able to communicate back to the Earth. Well, we already do that with designs here at APL with our software-defined frontier radios. And so we've got architectural approaches now that I submit that actually perhaps don't make me sounding so crazy. But there, of course, are other considerations, and many of you probably have already thought about half a dozen that you could, if we had an interactive conversation here, which I would love to entertain in the future, of where the issues are and the difficulties, and again, the no's that need to become yeses. And I'll just offer 3 very quickly. Test beds. They must be of the highest fidelity, without question. We must know that what we are developing new software capability to enhance the mission capability exactly mirrors the spacecraft that's in orbit. And those test beds must have the strongest configuration control. And then, of course, there must be complete longevity for the life of the mission. It sort of reminds me of the exercise that the New Horizons development team went through at APL. We had never flown a mission where its primary science would occur 9 years after launch. And so they wrote a longevity plan. They went through the thought process. They considered how long electronic media would reliably survive, and concluded, interestingly enough, back to my 34 years ago start, that pencil and paper actually have the longest longevity. You know, imagine laminating all of the written word and then having that available to the future. And so longevity needs to be thought through, and not just will the computers that we've designed on today still be functional, but will they be functional 30 years into the future when I actually want to do that software enhancement for Interstellar Probe. And then, of course, there's cost, and there's cost, and there's cost. And did I happen to say cost? Certainly, the test bed and the fidelity that I'm talking about is going to be expensive. Certainly, adding additional flight processor on the spacecraft, whether it be an equally powerful processor as it is with Solar Probe, or a lesser capable processor for my brainstem analogy, that is an additional cost. And all that I'm talking here is additional software development complexity, and it brings with it cost, which is why I'm speaking to you all here at the 2021 Flight Software Workshop, because the development techniques that are being suggested here need to come from you all, and the success will come from you. But the value of maximizing our assets, these fantastic machines that we build, that we launch, that do exciting discovery, which is why we do what we do, I think the cost considerations are worth maximizing, extending, enhancing, and augmenting for future value that, again, we can't even imagine today. Next slide, please. So where next and when? This view is our current solar system. If we look at some of the destinations that yet don't have a spacecraft against, and that's not to say that APL has been to every destination, because we certainly haven't, but collectively, as a spacefaring civilization, we've not yet done any significant discovery at Neptune or Uranus. And each, the initial concepts, the early concepts that I've seen, are 10 to 15 years of flight time. New Horizons brought fantastic imagery back from Pluto and Charon and the other small moons, and have teased and excited the scientific community to want to go see more, not just of the Kuiper Belt in general, but specifically Pluto. And those mission durations that I've seen are on the order of 25 to 30 years. And Messenger did fantastic science at Mercury, such that it's teased the science community into the excitement of a Mercury lander, which poses similar mission durations. And if I reflect on what's excited me in terms of getting into space, wanting to return and stay on the moon, not just to bring back samples of rocks, but actually to stay there on timelines of generations. Just standing here in front of you, I find it hard to believe that the first and last lunar landings all occurred, human lunar landings all occurred before I completed elementary school. So it's not just the out there, it's also within our own solar system. That this idea that I'm submitting and making an argument and a case for to you all and your talents and your capabilities, we'll go back to the solar probe example. What happens after mission orbit 24? So solar probe has a prime mission of 7 years. We're 2.5 years into it, 4.5 years to go. We've gotten quite close to the sun, but not to the final closest approach. That's the excitement in the science, the heliophysics science community. But do any of us believe that we wouldn't continue monitoring the sun with a healthy asset? We get to mission 24, and part of our solar probe is doing phenomenal and exciting measurements of the sun in 2-week chunks. What else would we ask of it? What else would we want to do with it? Of course, we're going to need to evaluate margins on the spacecraft. Processor margin being an important consideration. But we should anticipate and expect, and in fact, the scientists will challenge us to think about what more could we do? What else could we do? And how would we approach that? We talked briefly about Dragonfly. Currently, the mission is in the preliminary design phase. Next year, it will have its preliminary design review. So the development is still in front of the team. But we're talking about a mission, an octocopter that's going to fly on an extraterrestrial world and do it autonomously. We will develop the algorithms here. We will prove out the algorithms here. But there is an opportunity, and I'm certain an evolution of refinement to autonomous flying that we might want to take advantage of in that 9-year cruise from launch to its final destination. And just imagine what we might want to do 2.5 years after the primary mission is complete. There is no joysticking on Titan. I mean, right now, New Horizons at 50 AU away from the Earth takes about 14 hours for round trip flight time. So I say hello. 7 hours later, New Horizons, here's my hello. New Horizons says, I'm fine. 7 hours later, I hear the response. So Saturn, of course, being a lot closer than New Horizons is at the moment to us, but still will experience the fact that Dragonfly is going to have to fly on its own. And that's just fascinating from a software development, from a software advancement perspective. At the end of 2.5 years, what will we want to ask of it? I know the scientists will be very excited to discover more. As an engineer, I'd love just to fly over that next dune, fly over that next outcropping. And then if I bring it even more close back to here at Earth, I mentioned earlier the example of geostationary communications. What would we want to do 15 years after the next geostationary spacecraft are launching, for another 15 years beyond that? Well, we want more autonomy in those geostationary assets. Do we want to off-point the attitude control in a way that we haven't thought about before because we brought another asset to bear and we want to expand the service coverage area? What next weather spacecraft of the U.S. fleet will we move to a different longitude to actually then augment the monitoring of what is happening here on Earth? And how will we need and what will we want to do with additional software to accomplish that? And we haven't even begun, other than just mentioning it briefly, what we will want to do as we advance AI applications here in the terrestrial environment, and then say to ourselves, wow, I'd love to put that on this spacecraft, on this asset, and to get this benefit. Next slide, please. So, out there and beyond, the now of our flight software capability is the traditional and ongoing developments and the frameworks and the architectures that we do today. It's fascinating. We achieve exciting success. The machines that we as a community deliver into orbit are doing fantastically amazing things, both through launches and early mission operations and then through their full mission life cycles. The then, though, is the future capability, and only possible through what you all do in software development. As I started the argument with, the hardware that we deliver is the hardware that we have to use that's available to us to these end destinations. The Times spacecraft, which is another part of the APL success, launched in 2001, upper ionospheric monitoring. It is still functioning and providing critical science today, nearly 20 years later. The end of this calendar year will be 20-year anniversary for Timed. So both in what we do here in monitoring Earth and looking to discover future destinations, offers an opportunity for this community and with your creativity to, in the future, then bring enhancements, augmentation, and expansion of the capabilities to these machines that we bring today. And frankly, as we look into 30 years into the future, Interstellar probe on its journey, not yet to its final destination, we have to give considerations to the ground infrastructure and the equipment in place to be able to actually still operate interstellar probe. It won't be sufficient at that time for those durations to simply look for the online auction services to see if I can go find a 386 computer or the computers of the age that we're using today. Using the phrase that I had, or the statement that I had done earlier, our state of the art will be the archaeology of the future. How many of us are using the first personal computers that we bought for our homes to look at the first photographs that we digitized from our early photo albums? How many of us are still using the first computers that were handed to us on our desktops as professionals to get off of the pencil and paper and to actually now start doing engineering in the digital environment? We progressively have had to migrate and enhance and augment the tool suite that we're using to be able to leverage the experiences of our past to then be able to strengthen our future. Your community, this community of flight software developers, offers an exciting possibility to actually be able to do more in the future with what we do today. I greatly appreciate the opportunity to speak today to this forum and to sharing just one small idea, perhaps greatly flawed, but under the premise of I need to hear the no's to turn them to yeses. I hope it's resonated with some of this audience, at least a few, and I eagerly look forward hearing back through the forums of future software architecture trades, future subsystem design reviews, future computer architecture discussions, with the intent of enhancing our shared drive for space exploration and discovery. It really is what we do, and it really is who we are. And so, in closing, be bold, do great things, and make the world a better place. And Chris, I think I've saved some time for a few questions, if there are any. So perhaps we entertain those now, but thank you for everybody's attention.
Yeah, thanks a lot, Steve. And I was struck by a lot of what you said with regard to how do we adopt a lot of these future technologies when the time comes on these historic systems at that point without jeopardizing the mission. And I would make the observation that it's very hard and challenging to get it right the first time when you have all of the developers and you have all of the test beds that haven't collected any dust yet in the lab, and all of the tools are still currently state of the art and people are trained up on them. We are fallible and we make mistakes, and so that's a really important, significant challenge. And I think that maintaining, looking forward and having to meet that challenge, at an organization that has multiple assets that they're managing, and having to meet that challenge for multiple missions, perhaps simultaneously, that seems like it doesn't scale very well and just further compounds the problem if you have, teams of people who are training up on technology from this decade, and then other groups of people who are training up on technology on another decade. That seems incredibly challenging. It's not really a question, just more of
Yeah,
observation.
no,
Yeah.
but certainly it's an important observation, and it's, half of the idea here, the other one being expanding capability. We have, in some ways, stumbled into long duration missions. Kind as one of the examples I gave was likely a 3-year mission design, and is now uniquely still doing important climate monitoring or science monitoring, I should say, nearly 20 years later. And New Horizons for us, as you know, Chris, was the first entrance into a mission that its primary science would be 9 years after launch. And the outer planets, Dragonfly, looking at something at Neptune, back at Pluto or the Kuiper belts, those missions are 25 and 30 years in duration when you think about the transit times to get there, as well as the science opportunities and missions that are being conceived. And we've all seen as individuals the very rapid evolution of both computers and even most notably consumer electronics, which we actually now use in our workdays. We're going to need to plan for these missions to be successful, and you and your colleagues are the source and resource for those solutions. I just firmly believe it. You are the software developers. It's quite exciting. These are very exciting challenges.
Yeah, and another observation is that when the time comes for each particular mission, it's usually the case that the hardware that we're flying on, in particular the computing resources, are often, even at the time, they're relatively old technology, based on more commercial units that were available decades before. So I think the problem that you're describing is even further compounded, that it's, in some cases, it's not just having to reach back to the technology when, that was available during the mission, but it's often even, perhaps decades before that. And the software, and that's absolutely not a knock at all on hardware. That's just the reality of having a resource constrained system and resource constrained environment. But it's a little bit of a paradox that the software development and the technologies available during the development of that software, we use more state of the art or strive for that. So there's definitely a little bit of a paradox there. And yeah, so all right, I will get to, there's a couple of questions in the chat. Let's see. So very interesting vision. The main challenge as I see it is, how are we going to support new types of software which are usually require higher performance than can be delivered on hardware included at launch? Any hints at the direction on that?
Yeah, it's an important question. It aligns with the general category of, let's start talking about the nose. So often, Chris, to your point of leveraging the heritage computers, which obviously then give people confidence that the hardware is going to survive the radiation environments, as one example. Perhaps we need to push the hardware developers into maximizing and increasing capacity beyond what is required for the specific mission objective. And I know that might be considered antithetical to designing past requirements. But if the requirement becomes enabling future capability, then perhaps the only way to achieve that is by allowing additional resources. And yes, it'll be difficult to perhaps get a processor to operate faster than what it was fabricated to do. But it certainly could lead us to adding additional resources that in some ways are not required or dormant for what we believe to be of the primary mission. And I know as soon as I say that, I hear the argument. don't have the budget for that, don't have the time to do that testing. Nobody's going to be interested in it. And those are all factual statements for today's paradigm. But can we begin to change those with the recognition? An interstellar probe is a great example. 40 years at 10 AU a year, which we haven't achieved yet. So anything not as fast as that is going to take longer to the destination. It will challenge us and drive us to think about not only just electronics operating reliably with no human intervention for 40 years other than operating it, but it will drive us to think about what might we want to be able to see 40 years from now. It's an excellent observation, important question. I don't have that answer, but I'm excited that the conversation is beginning.
Yeah, and that I want to touch on that a little bit more. You certainly won't get an argument from the flight software community about wanting to get more resources. And in fact, it goes more, in addition to trying to support ideas of the mission that have not yet been conceived, but also we have a little bit of a paradox where we are trying to develop software that is highly reusable from mission to mission. And one of the a very effective way of doing that is through abstraction. And it's almost a necessary or a consequence of that it's, less efficient. So we are always looking to get more horsepower, more RAM, and it may be significantly more than what would have been needed to do the same function decades ago. However, being able to be more portable from mission to mission necessarily requires some of those additional resources.
Yeah, I'd like to believe that I will continue to increase my own intellectual ability as I go from today to the end of days. So I only have the computing resources that have been given to me, yet I'm optimistic and excited that I will continue to do exciting things. And that might to some seem like an overly simplistic analogy, perhaps true. It might have others to conclude the answer to the question that I posed a few times, am I crazy, to be yes, you are. But I have finite resources of which interesting things still remain ahead. And does a multiple processor rotation type architecture that would allow you to transform your software architectural approach to be more efficient, or does multi-core processing, parallel processing, additional RAM and memory to be able to do things in different ways than was conceived to the initial heritage architectural approaches, are those all pieces to being able to access aspects of, back to the human brain analogy, network connections and interconnectivity and intellectual aspects that yet have not been tapped. This is an exciting time that your whole part of the industry works within, because these are questions that will be in front of us, and certainly in the terrestrial systems that develop that we can then leverage to then apply to space flight. Fascinating future for us all, I believe.
Absolutely. Yes, that is a very significant challenge going forward. And thank you very much, Steve Thibault, for your very interesting keynote talk.